Welcome to Chapter 10, the second screencast, More Liquids and Solids. One thing that you should be sure you're able to do is to distinguish between breaking chemical bonds, which we've dealt with quite a bit in the past, and overcoming intermolecular forces, which is the subject of this chapter. So just as a note and a comparison and a distinction, overcoming intermolecular forces is something like this. Here are two molecules, and to overcome intermolecular forces, those molecules separate from each other, but the molecules remain intact. So let's look at that again. Two molecules, overcoming intermolecular forces means that the attractions between the two molecules are overcome, and the molecules get farther apart, for example. They go from a liquid to a gas, but the molecules are intact. Now let's contrast that with breaking chemical bonds. Here we have similar molecules and then some others as well. This is actually propanol, by the way, and these are oxygen. And propanol can not only go from liquid to gas and overcome intermolecular forces, but it can burn in the presence of oxygen, and here is breaking chemical bonds. So let's see that one again, and note what happens is when chemical bonds break, we start with propanol and oxygen. Bonds break, new bonds form, we produce water and carbon dioxide, but notice that these molecules are definitely not the same as these molecules. Whereas when we overcome intermolecular forces, these two molecules here are the exact same as these molecules here, they're just farther apart. Breaking chemical bonds, different molecules altogether. Okay, so let's now consider some examples, and the first one for today's screencast is the trend in boiling points for the group 4A hydrides. So we're dealing with the carbon family of elements, and we're going to graph their boiling points as we go from CH4 on through the other elements in the carbon series, in the carbon family, that are hydrides. So there's methane, CH4, second period central atom carbon. There's SiH4, GeH4, and SnH4. And we've graphed the boiling temperatures of those four compounds. Notice they're all the same type of compound, tetrahedral, carbon in the middle, silicon in the middle, germanium and tin, surrounded by four hydrogens, tetrahedral shape, all nonpolar, and as we go from the second to the third to the fourth to the fifth period for the central atom gets progressively larger, and as we would sort of expect, larger molar mass, larger molecule means more polarizable, means higher boiling point, and the only forces in play here are London dispersion forces because we have only nonpolar molecules. All right, well, let's try that with another group, this time the group 5 or 15 hydrides. So this is going to be the nitrogen family, the chalcogens, and let's see, we have NH3, PH3, etc. So there's PH3, ASH3, and SBH3. So we're going to progressively larger and larger molecules. Central atom surrounded by three hydrogens. There will be a lone pair. These will be trigonal pyramidal. There is some polarity, therefore, but the polarity is not big, and it gets smaller, and it looks like the size and the London dispersion forces effect is overcoming any polarity differences, and so we definitely see the trend of larger molecule means stronger attractions between the molecules and higher boiling points. I'm sorry about this, folks. It looks like NH3 isn't on here, but well, that's okay. Hopefully it's on the next slide. And note, we should be able to pretty easily predict where NH3 is because it's a smaller molecule, so we would expect it's going to have a boiling point of, I don't know, maybe negative 120 degrees Celsius or something. So hopefully it's on the next slide. Let's check. So is that where NH3 is? Oh my goodness, there's NH3. It actually has a boiling point of something like negative 20 degrees Celsius. Wow, that trend doesn't seem to be followed for the NH3, although it's followed for the other substances in this family. So what's going on? Well, let's hold off on that for a moment, and let's try a different group. Maybe this is just an anomaly. Let's try the group 16 or 6A hydrides, which is the oxygen family. Sorry, I think I said chalcogens before. The nitrogen family is, of course, the pnictogens, and the oxygen family is the one that is the chalcogens. So let's do the same thing for the oxygen family of hydrides, and it's going to be H2S, H2Se, and H2Te for the third period, fourth period, and fifth period molecules. These are going to be bent. Some polarity, but not a lot, not perfectly symmetric, and the trend seems to be as expected and as we've seen before, except, darn it, looks like I left one off again. The H2O molecule doesn't seem to be here, but hopefully it's going to be on the next slide, and again we should be able to predict what its boiling point should be. That H2O looks like it should be about negative 80 degrees Celsius. So let's check, is that on the next slide? Is it in the right spot? And oh, there it is, H2O. Oh yeah, that's right, that's water. H2O actually boils at 100 degrees Celsius. Way off, almost 200 degrees Celsius different than what the trend looks like. Man, now this one we know is right. We do know water boils at 100 degrees Celsius. It's a common substance we're used to, so something weird seems to be going on. Well, let's try one more of these hydrides and see if we just have maybe two anomalies. So let's do the group 7A or 17 hydrides, which are the halogens, and we'll spare you the suspense a little bit. HCl, HBr, and HI all are graphed in terms of boiling point. HF has not been shown. It sure looks like, based on the trends up until the previous two examples, we would say it would have a boiling point of maybe negative 110 degrees Celsius, but we're probably starting to get a little suspicious when one of those data points is missing. And HF, it turns out, actually boils at something like 20 degrees Celsius. So again, way, way off of the general trend. We have linear molecules, we have some polarity. It looks like in general the London dispersion force size factor overcomes polarity differences, but boy, not so in the case of HF. So what can we conclude from this? Well, here is sort of the summary of what's going on. We have anomalously, unusually high boiling points for the compounds NH3, ammonia, H2O, water, and HF, hydrogen fluoride. And the reason these are anomalously high, way higher than we'd normally expect, is that these are compounds that exhibit what's known as hydrogen bonding. And hydrogen bonding is a particularly strong attraction that involves, well, hydrogen, duh. But it also involves hydrogen that is specifically bonded to either nitrogen, oxygen, or fluorine within a molecule. And note that nitrogen, oxygen, and fluorine are all in the second row. They're all small atoms, and they're all highly electronegative. So hydrogen bonding is our third intermolecular force. We've already seen dipole-dipole forces and London dispersion forces. Our third intermolecular force is hydrogen bonding. Hydrogen bonding occurs when we have hydrogen bonded to oxygen, nitrogen, or fluorine within a molecule. Water is a classic example of a substance that undergoes hydrogen bonding. And as a generalization, if a molecule has hydrogen bonding capability, it's going to have extra strong attractions between its molecules and extra high boiling points, melting points, enthalpies of fusion, enthalpies of vaporization, all those sorts of things. Note that hydrogen bonding, even though we use the term hydrogen bonding, it's not actually a chemical bond. It's actually an extra specially strong intermolecular force, or ESSIMF. No, nobody ever really uses that as an abbreviation. And extra specially strong intermolecular force is a particularly cumbersome thing to say. So we use the term hydrogen bonding. Chemists use it, biologists use it all the time. But you should keep in the back of your mind it's not a true bond. It's just a really strong intermolecular force. One example of hydrogen bonding that's particularly worth noting is that water is a special compound with lots of unique properties, including that icebergs, water frozen, is less dense than the liquid and floats, whereas almost any other substance like benzene, when it solidifies, it's more dense and it sinks. And ice floating turns out to be, well, it's bad for the Titanic, but it's very good for fish because since lakes freeze from the top down, where then they get a covering of ice that is less dense than the water, what that does is it keeps, it's a sort of an insulating layer, keeps the rest of the lake from getting as cold and turning all of the fish into little fishsicles. So that happens to be a particularly good thing. And then, well, why does ice float? Because it's cold. Ice wants to get warm, so it goes to the top of liquids in order to be nearer the sun. Is that true? Look it up and find out. Oh, I should just look stuff up in the first place. You can learn a lot talking to me. Well, Calvin's dad is not the greatest scientist, does not have the best explanation of things. So let's provide a better one here. Here are some water molecules in liquid form showing the bonds between hydrogen and oxygen within the molecule and the hydrogen bonding, i.e. that extra specially strong intermolecular force from one molecule to the next. And when water solidifies, it makes this sort of open structure that maximizes the hydrogen bonding. So here's a hydrogen bond, here's a hydrogen bond, here's a hydrogen bond, here's a hydrogen bond between this molecule and that molecule and that molecule, etc. And this open structure is is less dense than the liquid, which is more dense, and so ice as a solid floats because of this more open structure. Water has really high boiling and melting points compared to any other molecule its size, which is critical for the existence of life on this planet. Think of what would happen if water was not a liquid most of the time within the range of temperatures we experience. Water has a really high specific heat and heat capacity, which has a moderating influence on climate. Water has a high enthalpy of fusion and vaporization, which makes it hard to turn from a solid into a liquid and from a liquid into a gas. And water is very polar, so it has high solubility for ionic and other polar substances water. And then we'll wrap this screencast up by noting that water can undergo capillary action and help draw water up the narrow tubes in trees, kind of like water wicks up a paper napkin, which helps get water up to the leaves. Has some very important aspects in biochemistry and lots more. And all of this is due to hydrogen bonding, which is particularly strong, particularly ubiquitous in water.